Hello, everyone, and welcome to Solar Turbines Success on Decreasing Cycle Time and Cost. You will learn how this team used aPriori data to convince their tool design department to work in a new way. My name is Christine Tusa, and I'm an account director here at aPriori. I am joined by Annabelle Castro and Isaac Alvarenga. Before we begin, a few housekeeping notes. The attendee lines will be on mute throughout the session. We will be taking questions through the presentation utilizing the panel in the event website. So not the Zoom chat, but within the event website. So please put in your questions there and we will answer as many questions as we can at the end of the session. You can access today's presentation in the Files panel. Let's begin.
Thank you, Christine. And welcome, everybody. We are very pleased to present today and very happy to show how we got a successful project with the help of aPriori. And yeah, I will start first by introducing us. Annabelle.
Hello, my name is Annabelle. I've been at Solar for almost 4 years, and I'm the aPriori modeler lead focusing on modeling.
Okay, thank you. And my name is Isaac Alvarenga. I've been working for Solar for over 6 years, and 4 of them are in support of aPriori. So yeah, we are very happy to present today what our project was. And basically, it's the premise of how we got to introduce aPriori into a design group. So basically, if you know the relationship between Solar and aPriori, is that we use the tool in the supply chain portion, the life cycle of a part. We basically use it to create a good manufacturing process that we can compare with our supplier. So now that we have been using it for around 5-6 years, we have been training the backlog, and now I think it's time that we move on from using it there to a design phase of a component. And to start this project, it was first the question about which group. We have many design groups in Solar, so it was a tough decision to make. And at the end, we decided tool design for 3 main reasons. The first one is that they don't follow the common path in the creation of a mechanical component. Basically, they don't go through the mechanical analysis, they don't go to the thermal analysis or the transient analysis. It's more like a process of designing and fabrication, not too much meetings for review. It's just a very straightforward process. The second reason is that we are talking that around 80 to 90% of these fixtures are fabricated in-house. We have a tool shop dedicated to create these fixtures. And the third reason is that for the amount of designs that we are talking around 200 to 300 annually, it's considered high for a design group in Solar. So basically we have a good amount of opportunity to find design opportunities. Talking about the fixtures, I know in other places you can call them tools, jigs. We basically use them for different operations within Solar, between lifting components, using it to machine components for inspection, or even sometimes we create tools for field operations. Okay, so now once the team was decided, it was a matter of, okay, where do we want to set up aPriori within the design of a fixture? And we know that aPriori allows the early visibility of manufacturability issues, but of course, to create a good cost model, we need the 3D CAD file. And after reviewing the process to create the fixture, we found out of these 2 days that kind of make sense. The first one is the creation of the concept. At this point, the designer has, I will say, a 90% completed 3D CAD file that is sent to the requester of the fixture for a review. And basically, in this period of 2 or 3 days, the requester has time to review it and do some recommendations if they want. So it was the perfect span and amount of time for us to enter with aPriori and even suggest more changes. And basically, we are doing it in a time where we have the ability to influence the design without too much hassle. Once it was decided, we move on to, okay, how we will create that communication and draft process and the process. And we basically draft this process that it's very simple and just, we will need to create that communication between the tool designer and the cost modeler. But it was another pivotal moment during the project of who would be using aPriori. We basically knew that the tool designer can use it, but we moved away from that idea because we didn't want to go through the learning curve for the tool designer. And basically because we have the cost engineering group next to the tool design group. So the communication, it was going to be very easy to manage. And for that communication and to create that relationship between the tool designer and the cost modeler, we came up with this analogy that, okay, we don't want to take power from the designer. At the end, he's the pilot and he will take the final decision on the design. And we want the cost modeler to work as the co-pilot, but to have another set of eyes to look at the picture and make recommendations. And from here, it was a matter of trying to merge different things in the project. We are talking that we have designers, we have cost modelers, we have aPriori, and we have the machinists in our groups that will be influenced by these new designs or what we can improve. So first, we started with designers. Here, the team had a doubt, and basically supervisors and management of how aPriori can help us. So basically, they weren't familiar with aPriori. So in their minds, it's like, we think that the process is working. I mean, we are creating tools. The tools are working in the field. The tools are working for what our needs for inspection. So what exactly can we improve, or how can you prove us that there is a room for improvement? So we lay out this exercise with the designers to basically uncover how, depending on the designer that is going to design the tool, he will have different perceptions of how that tool should be made and designed. So basically, the exercise is very simple, where they were 5 steps. With one, it was that we will play the role as our requesters, and we will request a fixture for this part that we created as a mock-up component. For the exercise, we have 5 designers that were going to work along without reference, and every designer, it will come up with a solution for this component. After this, we had a meeting where in the meeting, every designer explained their logic and their process that they follow to come up with their unique design. And in that meeting, we also had questions about, well, let's talk about what you think about safety, what you think about cost, machinability, and functionality, how you prioritize those 4 things that for us, we think it's important and the designer should take in mind. At the end, we have the conclusions. Obviously, it's not that the designers are right or wrong. It basically, we just want to lay out that opportunity. So I'm going to talk about the conclusions that we got from that exercise. And the first is that we come up with this idea that basically every designer has a starting point. And this starting point is made out of 3 things. We have first, the tool requester information. That is basically the request. And sometimes the requester will explain the function that the tool needs to accomplish. And sometimes it provides a sketch or a more detail of the process for the fixture. Obviously, this is a communication, and we know that communication flows in both ways. So basically, even if you are, if we have 5 designers, every designer will perceive that information initially very different from one and another. The second thing that we found is the boundaries of the design. So basically, these are natural limits that the designer will need to work with them to create the fixture. And we are talking about, for example, machine dimensions. You cannot exceed the dimensions. And for example, the weight, if the fixture is with an overweight, it's not, we are not able to use it to accomplish the purpose of it. And of course, if this fixture is interacting with the shape of the engineering part, we are not able to modify the engineering part. Basically, the designer needs to adapt the design to it. And the third thing is the knowledge and experience. Same thing. Every designer has a different understanding of the machines, of the fixtures that they have seen, that they have designed. They have different levels of knowledge about machining and also standard parts and GD&T and tolerances. Basically, these are three things that we consider that the designer doesn't have control or doesn't have full control. And every designer, this is the starting point to create the fixture. After this, we lay out in general, the process that they follow to create the fixture. I won't go too much into the detail that they follow, but the important thing, it was about the concepts, how they treat and how they involve those concepts when they are designing the fixture. So we noticed that safety and functionality, those were considered in every step when you are trying to design a fixture. Obviously, safety is our first priority, so that's perfect. Functionality, obviously you want to design a fixture that will accomplish their purpose, but we noticed that machinability and cost were almost at the end, and not all designers were considering them. And basically, these four things is what we consider things that the designers has control over them to create the fixture. And jumping onto the last slide of the exercise, it was well, now that the tool designer has these 7 things to work, they come up with 6 different designs for the same issue, the same request that it was made. And as you can see, we have totally 6 different designs. Some are very similar, they share some things, but basically kind of lays out the different perspectives that the designers will have. We would love that every designer it was able to create a 3D model, so we would basically run them through aPriori and have like real numbers, and then work with supply chains to cost the real price of the material. There wasn't time for us to do that exercise completely, but here we kind of lay out the difference of the 6 fixtures. So basically, every fixture will have a different cost for the price of the material and a different cost for the machining portion of it. And talking about time, they will correlate and will have different time to finish the drawing and different time to complete the fixture. So basically, the main and key question was, are we always designing the most optimal fixtures in terms of function, safety, cost, and machinability? Well, as the example lays out, maybe yes, maybe not, or even if we are doing it, there could be improvements that definitely can be made to the fixture. And after we did this exercise, it kind of narrowed down that opportunity, and it showed to the supervisors and management that, oh, okay, yeah, basically there is room for improvement after you show us this. Okay, jumping on, we run to the aPriori portion. So obviously we will need to adapt aPriori to our tool shop. And to do that, we created certain rules for the cost modelers that basically, well, we don't have the capability of 5-axis mill, so don't even cost parts through that routing. 4-axis mill, we don't have it, we don't use it. For holding device, just use the common ones, vice, table clamping. We remove programming time, as it is not very common for the machinists to go and program. It's just basically that they can create paths right next to the machine. Simple paths, for example, milling or a hole pattern. And obviously we will need to adjust the stock size and material to what the blueprint is requesting. In terms of accounting, we just changed and decided that we will use the TurboTech rate or rate, and we will use the high material cost library for a good approximate of the material price. After this, we went on with the machinists to talk with them, and basically we wanted to narrow down even more what they have seen in the past years as issues for them or opportunities. So we basically did some questions to them. They were very kind of us to show us some examples, and we started to look at the information and what we needed to review with a priori and analyze in terms of a picture. So basically, we did questions, for example, that what increases the setup time of the part the most, or what features take the most time to machine on a male part. And at the end, we got the conclusion that we basically need to focus on three things: maximize material utilization, find features with non-value added, and find machining issues. Obviously, talking about machining issues is not that it is impossible, but sometimes you get to see a part that it maybe has too many setups, and it's like, are they really necessary, all those setups? Or for example, you have a pocket, and as the machinist it was saying, it's not that this pocket it's impossible to make, but can it be changed to be easier, to be simpler for us to make it? So those were basically the things that narrowed down in this project with the help of the machinist. Okay, after we had our talk with designers, we modified aPriori, we went on to talk with the machinists, we were ready for our aPriori pilot. So we basically run the pilot at every request that it was created for the designers. We will cast it in aPriori. This lasts over a month, and we cast 9 fixtures. So next I will show the results of it. We basically create an acronym to categorize them. That it basically has design opportunity or it doesn't have design opportunity. And from that exercise, we find out that from 9 fixtures that we cast, 7 had design opportunities, 2 that didn't have. And from those 7 that had design opportunities, in 3, we were able to change the design. They were accepted by the designer and agree with us. And when we were unfortunate with 4. And the last chart on the right, well, every fixture can have more than 1 design opportunity. So basically our numbers were that from those 9 fixtures, we did 16 design recommendations, and at the end, 4 were accepted. Okay, and important thing, the once that we were running the pilot, we started to understand that we would also need a guide for cost modelers, because as I mentioned before, Solar was only using aPriori in the supply chain portion. But now that we are moving into the design, it's like changing your mentality and your chip of what you are trying to find with aPriori. So at the same time that I was doing the pilot, I started to think of how we would show this information to the cost modeler, so when they got the opportunity to cost this part, they can focus on these things. So we basically start to laying out this type of examples, and this is a re-example of a picture that we got to modify. And it starts like this. For example, if we want to maximize the material utilization on a fixture, we need to understand the formula of what we are talking about. And basically it's your material cost plus the cost of removing the material. Almost all our fixture are machine, and that will get us our final cost. So basically one of these 2 variables need to decrease to get cost savings. Obviously those 2 variables are made of more variables that are below. And for example, price per pound, that is controlled by market. So the designer doesn't have the possibility to change something there. But talking about initial stock dimensions and features of the part is where the designer has the opportunity to change them to create a cost savings. So going further into the example, we had this leg that is kind of like a support of the fixture. And we find out that the utilization, it was only 45%. And we can see the machine mass, that it was 2.84 pounds that it was being machined of this. So if we see it in terms of numbers, it's like, for example, if you are paying $50 for your initial stock, well, you are converting out of those $50, 27.5 to chips and paying an X amount to remove it. Okay, so as the cost modeler, we did and go into focus on the proper thing. So basically, we check the initial stock dimensions. So everything looks good here, talking about the perimeter and talking about the thickness is not even a surface that is requested to be machined. But now, evaluating the component, the features of the component, it was a matter of, okay, let's start by taking a look to what each feature represents. So basically, we saw the holes and we understood about what the main objective of the holes were. And we started to wonder about the perimeter of the part. And I think we thought that, okay, this cut makes sense because basically what the operator is doing is that it's taking the injector assembly and putting it on the fixture. So, okay, we are good with that. But how about the inside cuts? And I think it's a very good thing that for us modelers, we are not like very comprehensive of exactly the objective of the fixture, because now we have the opportunity to start asking the questions and not assuming. So basically we are looking at the fixture and just wondering why this, why that. In the case of the designer, he's taking the decision and he's assuming those things beforehand. So at this point, our recommendation for the designer, and is basically just laying out like, hey, this part has low utilization and we are not sure for what exactly is the purpose of the inside cuts. So we went through our process. We had the meeting with the tool designer, and he came up with an answer for the inside cuts. And he told us it's basically to reduce weight and allow ventilation during the welding operation. Totally fair, and it makes sense. But basically, it's now up to decide if it's a function, if it's very important for the fixture, or if we want to reduce or increase the manufacturability of the component. So basically now the cost modeler came up with the question of, hey, how many pounds are reduced with the inside cuts? Or is it even necessary, the reduction of the weight? I mean, I think at this point it's like, are you considering that this fixture will be lifted up by the operator by hand, or are you using a crane to do it? And the last question is, well, how much ventilation is needed for this fixture? After those questions that we did, I think the designer understood that, okay, yeah, maybe we can get rid of them and no problem. It wouldn't be too much a hassle to take them off, and it would save us time. And just to complement on this fixture, we had another component where basically it's a very simple component. And the thing it was that it was managing multiple setups. So basically you can see right here that, okay, you need a setup to create the perimeter of the part, but then you need a setup to create this hole, then you need another setup to create these holes. And on the other face that we're not able to see, there are a couple of holes right there. But after that, we will need a setup to create these flats. So these flats alone are increasing the number of setups. And when we took a look at where this component it was located right here in the middle. And then again, we talked about it during our meeting with the tool designer, and the tool designer came up with the answer. Well, it's a safety measure to avoid the sharp corner during the installation of the hoist ring right here. And it's totally fair and understandable, but taking into the advantage that we are already modifying this component right here, well, why don't you extend this portion right here to cover that edge? And basically, from that point, we are avoiding to machine those two flats on the component. And then again, the designer agreed on it, and we could move on to change this component. And that basically wraps up how cost modelers need to change the mentality from costing parts to just obtain the right manufacturing process to now looking at design opportunities. And after that, we'll just we did a side-by-side comparison. I know it's not a big savings, but we are looking at in terms of design volume. So basically, we go for the volume and not so much by each component. After that, we got to the conclusion of the pilot. We basically did the numbers and extrapolate from our sample to the overall numbers each year. And we found out that at the end, we could have around 100 features that could see future benefits, like reducing manufacturing times, reducing manufacturing errors, reducing design changes after completing the drawing, reducing machining doubts and questions. And obviously, designers learn from experience. I think after 1 or 2 times that you are telling them like, hey, increase the radius, hey, check the stock again, they got to the idea of those things beforehand and completing the fixture. And obviously at the end, what is more important? Well, generating savings. And after the pilot, it was just a matter of implement it. And now Annabelle will show us some successful cases that we've been having.
Thank you, Isaac. Well, the first successful case I'm going to show you is the next picture. This one clamps the injector in 3 points for an inspection operation. It also has a hose which is needed for a flow test. With the initial concept, we noticed that the utilization was only 18% due to all the external and internal stock being removed. This realization was crucial to go look in detail at the stock and machine features to identify what was really essential. Shown in red is the peripheral of the original stock size. Besides that, it had a complex feature all around this perimeter. The function was to locate the hose, but the feature wasn't possible to fully machine the 2-axis lathe since it had an inclination, so the setup times were very high. The design recommendation was to maintain the outer diameter since it didn't interfere with the design intent. This increased the utilization to 42%, and to accommodate the hose, the inclination was only machined in the portion of section needed by the hose. At the end, fewer features to machine and less complexity lead to a lower price. Next slide, please. In the next example, the original design showed a 90-degree corner. This could increase the manufacturing time, and since it's not really needed, the suggestion was to change the corner radius to maintain the tool diameter. And so a 0.5 radius was added. Next. The same can be seen in the following example. The radius was extended for all the rounds inside the pocket corners. And finally, a common suggestion that is made and in these and other components is that changing the geometry to a simpler one when it doesn't affect the design intent. This is crucial because machining times are lowered and it always is reflected as cost savings. Now let's go back to Isaac.
Thank you, Noel. And I think just by final comments, and basically our next steps that we will follow within Solar Turbines, it's basically trying to implement this process now on a different design group. Another thing that we want to accomplish is to get designers to use the tool. Basically, right now we are supporting it with our costing group, but we want to move forward and for them to use the tool. And of course, we are aware of the tool that aPriori offers as design to cost or cost insight. But basically, right now, we want to create that engagement between designers and aPriori. And I think once the designers have that trust of using aPriori and how they can accomplish different things and results, we can move forward onto those tools. And yeah, I would like to say thank you to the tool design groups for being open to this idea and accepting the project. And I think that concludes our presentation. Thank you.